In 1677, a German philosopher wrote something that sounds absurd. He said that one day, when two people disagreed about anything at all, politics, ethics, science, they wouldn't need to argue. They'd just sit down, take out their pencils, and say, "Let us calculate." His name was Gottfried Wilhelm Leibniz, co-inventor of calculus, designer of a working mechanical calculator, and one of the last people in history who seriously believed he could fit all of human knowledge into a single symbolic language. He called it the Characteristica Universalis. Leibniz didn't invent this dream alone. 20 years earlier, the English philosopher Thomas Hobbes had written the sentence that lit the fuse: "By reasoning, I understand computation." If that sounds modern, that's because it is. It's basically the thesis of the field we now call artificial intelligence. Here's the wild thing. The prehistory of AI runs almost entirely through people who never saw a computer. AI is not a computer science story. It's a story about logicians, mathematicians, and philosophers slowly figuring out what thinking actually is, so that one day a machine could do it. For Hobbes and Leibniz, reasoning meant following rules. But what are rules made of? That question sat there for almost 200 years, until a shy, self-taught English school teacher named George Boole decided to answer it by turning logic into algebra. In his 1854 book, The Laws of Thought, Boole showed that sentences like, "The cat is on the mat," could be combined using and, or, and not, exactly like numbers are combined with plus and times. Logic, he showed, wasn't philosophy. It was math. Boole also formalized the oldest trick in reasoning, modus ponens. If it's raining, the ground is wet. It's raining. Therefore, the ground is wet. Trivial, right? Except modus ponens is the engine. Feed it facts and rules, and it manufactures new facts, correctly, every time. But Boole's system had a catch. You had to write a separate rule for every specific case. Two men, Charles Peirce in America, Gottlob Frege in Germany, independently fixed it in the 1870s and 80s. They added variables and two little symbols, for all and there exists. Now you could write one rule that covered everything. For all A, B, and C, if A is to the left of B and B is to the left of C, then A is to the left of C. One line. Infinite applications. Predicate logic was born. If logic was this powerful, maybe it could do more than organize sentences. Maybe it could rebuild mathematics itself. That was the bet Bertrand Russell and Alfred North Whitehead made in 1910, with a 3-volume book called Principia Mathematica. Famously, it took them about 360 pages to prove that 1 + 1 = 2. And then, in 1931, a 25-year-old Austrian logician named Kurt Gödel published a paper that quietly set fire to the whole project. He proved that any formal system powerful enough to describe basic arithmetic must contain true statements it cannot prove. The dream of a complete mathematical foundation was dead. It should have been catastrophic for AI before AI even existed. If logic itself has blind spots, what hope is there of mechanizing thought? But the opposite happened. Gödel's proof forced mathematicians to ask a precise question they'd never formally answered. What exactly does it mean for something to be computable? The answer came from a 24-year-old Englishman, Alan Turing, in 1936. In a paper titled On Computable Numbers, Turing imagined a simple machine, an infinite tape, a read-write head, a few rules, and he proved that this imaginary device could compute anything that can, in principle, be computed. At almost the same moment, the American mathematician Alonzo Church had reached the same conclusion using a completely different system called the lambda calculus. Their results lined up perfectly. The two frameworks became known as the Church-Turing thesis, and with it, computation finally had a definition. Then history intervened. Turing spent World War II at Bletchley Park, helping break the Enigma cipher and almost certainly shortening the war. When he came out the other side, the world had something it had never had before. Actual, working electronic computers. Now the dream had hardware. In 1950, Turing wrote another paper, this one for a philosophy journal. He asked, "Can machines think?" Then immediately declared the question meaningless. Instead, he proposed a game. Put a human and a machine behind a curtain. If you can't tell which is which from the conversation, the machine is thinking. He predicted that by the year 2000, computers would play this imitation game so well that an average person would fail to spot the machine 70% of the time. He also predicted people would be able to talk about machines thinking without being laughed at. He was early, he was not wrong. While Turing was asking whether machines could think, two Americans were asking a stranger question. What if the brain itself was already a machine? In 1943, a neurophysiologist named Warren McCulloch and a self-taught 20-year-old prodigy named Walter Pitts published a paper that changed everything. Their paper described a mathematical model of a neuron, a simple on-off switch, and showed that networks of these artificial neurons could, in principle, compute any logical function. The first neural network, 70 years before they became fashionable. And right there, before AI even had a name, the field split into two camps. It's never really fully reconciled. On one side, symbols, logic, rules. On the other, neurons, patterns, learning. Every argument in modern AI traces back to that 1940s fork in the road. Back in symbolic land, a Bell Labs engineer named Claude Shannon was quietly becoming the most important person you've never heard of. He'd already used Boolean algebra to design digital circuits. In 1950, he wrote the first serious paper on teaching a computer to play chess, but the real breakthrough came from two psychologists turned computer scientists, Alan Newell and Herbert Simon, working with programmer Cliff Shaw at Rand. Over the Christmas holiday of 1955, they built a program called the Logic Theorist. Simon walked into his class in January and said, "We invented a thinking machine." The Logic Theorist was not a metaphor. It was a real program that proved real theorems from Russell's Principia Mathematica, 38 of the first 52. In a couple of cases, it found proofs that were more elegant than the originals. Russell was reportedly delighted, which brings us to Hanover, New Hampshire, summer of 1956. A 28-year-old Dartmouth professor named John McCarthy sent out a proposal he'd co-written the previous September. His three co-authors were Marvin Minsky, Nathaniel Rochester of IBM, and Claude Shannon. The document had a title that had never existed before. McCarthy had chosen the phrase artificial intelligence deliberately. There were already fields called cybernetics and automata theory and complex information processing, and he wanted out of all of them. He wanted his own name and his own conference. He got both. The proposal contained a single founding sentence that still defines the field. Every aspect of learning or any other feature of intelligence can be so precisely described that a machine can be made to simulate it. It's either the most optimistic sentence ever written or the most prescient, possibly both. For 2 months, June through August 1956, about 20 researchers cycled through Dartmouth College. Newell and Simon showed up with the Logic Theorist, the only working AI program in the world. They had debates. They disagreed about almost everything. The workshop ended without consensus, which is appropriate. But when they left Hanover, something had shifted. The dream Hobbes had sketched 3 centuries earlier, that Leibniz had written poetry about, that Boole and Frege had given teeth to, that Gödel had scared and Turing had redeemed, that dream now had a name. Artificial intelligence. Everything that has happened in AI since, every expert system, every chess win, every self-driving car, every large language model, is a footnote to that summer. Not because Dartmouth solved anything. It didn't. Because Dartmouth made it legitimate to try. And if you go back and read Leibniz's "Let us calculate," that strange, confident, centuries-old sentence, it stops sounding like a philosophical dream. It starts sounding like a prediction. The people who built I didn't invent the idea, they just finally built the machine.